What I typically do in class when we cover section 5.2 is I pass out this handout because I'm going to go over this problem on the board, but it involves so much writing that I want you to be able to pay attention to what I'm saying when I work this problem out on the board without having to frantically write everything down. So this handout you're looking at, I'm going to do this problem and you can just follow along without having to try to write anything down because you have this right here, which is essentially what I'm going to do. Now, because there's so many different ways you can work through this, when I do it on the board, it's not going to be exactly like this because there's just different variations of, different orders that you can do the steps in. But it'll be essentially be this. So this gets ahead of the game a little bit because we haven't talked about the fundamental theorem of calculus yet, but we're going to very soon. So what we have to know at this point of section 5.2 is that evaluating an integral like this is a lot of work. If we have to use the limit definition of an integral, it's just there's a ton of work involved. So I'm going to work through this one in a second, but this is essentially the work that you'll see, but I'll be explaining the steps as I go. But before this, I'm going to show you how easy it is by looking at the one on the back here. If you have the fundamental theorem of calculus, which we'll have very soon, then evaluating this integral is really simple. Basically, we'll find out that the fundamental theorem of calculus says to evaluate this integral, we take the antiderivative of this, which is right here, right? If you use the power rule, this goes up, right? This goes up to 3, then you divide by 3, which gets us here. And this x should become x squared, then you divide by the 2, so the 2's cancel, so you get here. The antiderivative of negative 5 is negative 5x. And then what we do is the notation changes a little once we take the antiderivative of this here, then we don't have this sum anymore. Now we have this notation here, which is basically saying I'm going to plug in the 4 into here for x. Then I'm going to subtract what I get when I plug the 1 in. So in section 5.3, we'll learn how to do this, and we'll just see that it's kind of an easy process to get an answer of 21. But before the fundamental theorem of calculus, when we're stuck in section 5.2, then we have to do it this way. So without the fundamental theorem of calculus, then we have the same problem. We have all of this work involved. So what I'm going to do on this video is just show you how to do this. So again, just you have a copy here that I emailed, so you don't need to write any of this stuff down. I just want you to be able to follow along as we go. So let me write down the original problem here. We want to evaluate x squared plus 2x minus 5 dx between 1 and 4. And remember, just for notation, whenever you have this integral symbol, we need a dx. So to get started here, this integral is equal to the limit of a Riemann sum and we'll go f of x sub I delta x. And you can see that in this case, the sample points we're using are going to be the right endpoints, because when we plug in 1 to n, our first one is going to be x sub I. And if you remember, if we go from a to b, a is always x sub 0. So we're starting at x sub 1. We're going to go to x sub n. So we're using the right endpoints. And as long as you take the limit, it doesn't matter. It doesn't matter where you start. But we're, for this example, using the right endpoints. So we've got, let's see, x sub 0 will be 1. And then x sub 1 would be 1 plus delta x. So let's figure out what delta x is. Well, delta x is b minus a over n. So in this case, b is 4, a is 1 over n, gives us 3 over n. Right, so this is a and b, and delta x, just by definition, is b minus a over n, so we get 3 over n. So if we're going to start at a, right, from a to b, x sub 0 will be a. So x sub 1 would be 1 plus delta x, which in this case is going to be 1 plus 3 over n. Then x sub 2, that's going to be 1 plus 2 delta x, or in other words, 1 plus 2 times 3 over n. And if we were to continue and just get some standard point here, x sub I, that would be 1 plus I times delta x, or in other words, 1 plus I times 3 over n, or 1 plus 3i over n. So we're going to need to know this. We need to know delta x, because we're going to have to plug these into our formula here. Right, so this is a limit definition of an integral, which is a limit of these Riemann sums. So f of x sub I, well, remember what we've got here. Right here, this is f of x, right? That's f of x, that's our function. So f of x sub I, we're going to plug x sub I in for all of these x's. And x sub I, what is that? That's right here. Right here, this is x sub I. So we're going to have to plug this in, x sub I, into these x's. And then dx, delta x, then is right here, 3 over n. So to integrate this, we need this. So let's rewrite this now and fill in what we've got. Make a little more room here. So we could say, okay, get to the pen here. So 1 to 4, x squared plus 2x minus 5 dx is equal to the lit as n approaches infinity. And right now I'm going to plug in, f of x sub I. So basically I'm going to write f of x, but wherever there's an x, I'm going to plug in x sub I. So this would give us 1 plus 3i over n squared plus 2 times 1 plus 3i over n minus 5. And then that, so far I've got f of x sub I, and I need to multiply that by delta x, which is 3 over n. So you get times 3 over n. So we're about to go through a whole lot of work here, but keep in mind the entire time, look how easy this is. I mean, this is a polynomial, second degree polynomial, and we're going to go through about a page and a half of work for this. So if this changes at all, like if there's a square root in here, or a logarithm or a trig function, then this is just like so much more complicated. In fact, it gets to the point where it can't really be done, or can't be done without a room full of geniuses. So we're going to quickly see that without the fundamental theorem of calculus, we would not be able to integrate very many of these functions, because this is just an easy polynomial function, and it's going to take a lot of work. So basically what I'm going to do in the following steps, I'm going to square this, distribute this through, then distribute this through, and clean it all up. And no matter how many times you do this, it seems like you always do it in a little bit different way. So if you if you look at the handout later, you'll say, for sure, I'm going to do it a little differently, just because there's just so many ways you can do it. But we'll all get to the same spot. So I'm just going to walk through this. Then we're going to find out we've got some we've got some problems because we're going to get these i's involved here. We need to figure out how to work with those. So we'll talk about that when we get there. But for now, I'm just going to expand all of this. So I need to make some room. And I'll just kind of walk you through it as we go. So this is equal to, the limit is n approaches infinity of the summation from 1 to n. So if I expand that binomial, we get 1 plus 6i over n plus 9i squared over n squared, right? Because I'm basically just foiling this. So take two of these, line them up and multiply them together, and we get this. And then I'm going to distribute the 2 through there. So that would give us plus 2 plus 6i over n minus 5. And then I've got the 3 over n here that still has to get distributed. So let's see what we've got. I'm going to look for like terms here. So we've got, let's see, 6i over n, 6i over n. And of course, we've got these numbers that can be combined. So that would give us 9i squared over n squared plus 12i over n. And then we've got minus 2 times 3 over n. So I'm going to distribute this 3, distribute this through here. I'm also going to separate, like this here, really isn't this the same as 9 over n squared times I squared? So I'm going to separate those a little bit because we're going to have to separate those eventually anyway. So, see, moving up here, we get, this is equal to the limit as n approaches infinity of the sum from 1 to n. So I distribute this 3, so that would give us 27 n cubed I squared plus 36 n squared I minus 6 over n. So it's getting a little better looking, but here's where the first problem comes in, this I squared and this I, and how do we deal with those? Well, that took somebody else. That took some discrete mathematics to deal with those. And I make a little room here, maybe off to the side. So in the appendix, in Appendix E in the book, some of these things that I write are proven in there. So we need to know a couple things. We need to know that the summation from 1 to n of I, in other words, think about what this says. This says if I start at 1 and go to n and I keep adding I, so it'd be like 1 plus 2 plus 3 plus 4 plus 5, so you add up all these numbers. Well, you end up getting n times n plus 1 over 2. So just to see, let's see if it works. I equals 1 to 4. So remember, this is summation, starting from 1 going to 4, and you just plug it in here and do what it says. This is easy because it's just I, and then you add it. It's always going to be added, so we would get 1 plus 2 plus 3 plus 4. If you add that up, we get 7, 8, 9, 10. So we get 10. So let's just see if the formula holds. So this is saying the formula is take this n and multiply by the next number and then divide by 2. So this is going to be 4 is our n. So according to the formula, it'd be 4 times 5 divided by 2, which does work out to be 10. There's a story of Carl Gauss. When he was 10 years old, he discovered that formula because he was told by his teacher, the story goes anyway, that he was always getting done with all of his problems really quickly. So the teacher was frustrated. He was 10 years old. The teacher said, why don't you just go to the back and add up the numbers from 1 to 100 and tell me what you get. The teacher was thinking that would be something to keep him busy for a while. But the story goes that he walked towards the back of the room. Before he got there, he turned back around and said, the answer is 5,050. And his reasoning was, if I were to add all these numbers, I'd go 1 plus 2 plus 3 plus 4, and he'd go all the way to 50, and then he would have to add 51, and then go all the way to 100. So this would be like a 99, and he was thinking, really, I've got 101. These all add up to 101, and I'm going to have 50 of them. So he did some arithmetic in his head and came up with the answer. So you sort of figured out this formula when he was only 10. So not bad for a 10-year-old. But for us, we just need to be aware of this formula, because we're going to have this I to deal with, but we also have I squared. So there's another one we need to know. We also need to know, that is the ugliest summation I've ever seen. Okay, let's try that again. The summation, I equals 1 to n of I squared. Well, if you add up a bunch of squares, you end up with n times n plus 1 times 2n plus 1 all over 6. And these formulas can be proven using mathematical induction. And then there's one for the cubed formula. It's in the back also. But you can see that there's just a tremendous amount of work here. So even when you get here, even if all this makes sense, now you have to deal with these. So then you have to figure out these formulas. So what we're going to do, we have to deal with this I squared and this I, and we can do that by making this substitution. And we can do that by breaking these up into pieces. So to do that, I'm going to make a little room here. I'm going to just put in a step in here, and we're going to take the limit as n approaches infinity. And I'm basically going to take these summations one at a time. Like instead of the sum, it turns out that the sum, or the sum of all of these, the summation of all of these sums is the same as the sum of all the summations. So I can individually take these sums. So doing that, we would get I equals 1 to n of 27 over n cubed times I squared, plus the summation I equals 1 to n, 36 over n squared times I, and then minus summation of I equals 1 to n of 6 over n. Then, with these summations, since this term here, or this 27 over n cubed, this factor actually, has nothing to do with I, we can move this out in front. So these things that don't have an I can go in front of this. And this even can go in front of this also. We'll have to figure out how to deal with this one in a second here. But basically, so this will give us equals a limit as n approaches infinity. We get 27 over n cubed times the summation I equals 1 to n of I squared, plus 36 over n squared times the summation I equals 1 to n of I, minus 6 over n times the summation I equals 1 to n. This ends up being 1. Okay, so it kind of makes sense if you think it's a little bit like the distributive property. If I bring this over here, I'm kind of like, I have to be something equivalent. So if I were to multiply this by 1, I still get back here. And then just think of what this says. So we know what this one is because we've got this formula for I squared, right? We know this can be replaced with this, so that's going to allow us to get rid of this one. And this one here also, I equals 1 to n of I can be replaced here. But this one, think about what this means. It means we're going to take, this is not I, this is just 1. So we're going to go from 1 to n of adding up all of these 1s. So basically, if you just think about what that is kind of like saying we've got 1 plus 1 plus 1 plus 1 n times, right? N times we would do that. Because again, this is just a 1 here. So we go through the process, we take this 1, we keep adding it. So n ones is really just equal to n. So this thing is just equal to n. So if we start to replace these, get the limit as n approaches infinity. You guys see why the fundamental theorem of calculus, when we can avoid this, makes this so nice? Because this is really, this is a nightmare, and this is just a really easy problem. Right? So if the problems are difficult, it's either impossible to do this way or very difficult to do this way. So this, I'm replacing this thing here with this. I'm going to do the very similar thing here. So then we get plus 36 over n squared times n plus 1 over 2, and then minus 6 over n times n. Okay, now we can do a little bit of canceling here. So this n will take one of those out to make that n squared. This n will make that n, and this n will just make that 6. So that will give us the limit as n approaches infinity. And we can do a little bit more here. Okay, so 3 goes in here twice. It goes in here 9 times. 2 goes in here once, goes in here 18 times. So that would give us, let's go 9 halves. I'm going to write this way on purpose, because it'll help us with our next step. This is going to be 18 n plus 1 over n, and then minus 6. Believe it or not, we're getting close. So I want you to pay attention to this a second and just think, isn't it true that n squared is just n times n? So if I really wanted to, we could write this way. The limit as n approaches infinity, 9 halves times n plus 1 over n times 2n plus 1 over n, right? Because when you multiply fractions, you go straight across. So this times this times this, this times this times this. 2n times n is n squared, right? So really this is equivalent. Then we get plus 18 times n plus 1 over n minus 6. And now we need to look at each of these. Isn't it true that n plus 1 over n, just do this off to the side here, n plus 1 over n, isn't that the same as n over n plus 1 over n? Or in other words, 1 plus 1 over n? Right, isn't this just 1 plus 1 over n because we break it up this way? Right, common denominator means the answer to this addition problem would be n plus 1 over n. Right, we're going the opposite direction. And likewise, this could be 2, right? 2 plus 1 over n. So I'm going to rewrite these. I'm going to write this as the limit as n approaches infinity, 9 halves times 1 plus 1 over n. This would be 2 plus 1 over n, 1 plus 1 over n minus 6. Right, so I'm just algebraically rewriting these in a way where we can take the limit. Because if you look right now, the way it is right now, I can't take the limit because I would get infinity over infinity, right? Infinity over infinity. But like this, algebraically, this is the same as this, and this is the same as this. But at this point, I can actually take the limit. Right now, we can take the limit. As n approaches infinity, doesn't this term just go to 0? N gets as big as we want. We could make this term not even matter. So we can take the limit right now. That will go to 0. That will go to 0. And that will go to 0. So once we take the limit, I'm not going to write limit anymore. We already took the limit. We get 9 halves times 1 times 2 plus 18 times 1 minus 6. And 9 halves times 2 is just 9 plus 18 minus 6. 9 plus 18 is 27. Minus 6 gives us 21. So we get the same answer, but it'd take a whole lot more work and a whole lot more time than when we use the fundamental theorem of calculus, which we'll learn about in the next section. But one more thing I need to mention here is the answer in the back of the book on number 29 is wrong. Number 29 in the back of the book, it's real close. They just forgot a little bit. So I'm going to write what the answer should be. So it should be summation I equals 1 to n, 4 plus 1 plus 2i over n. And it's squared. The book forgets to put that little square there. Times 2 over n. That's 2 over n. So when you look in the back of the book, they don't have this square. We need the square there. So keep that in mind with number 29. And then there's a couple of them in the book where they want you to go through this process that we just went through. There's just a couple of them, just so you can appreciate when we get to 5.3 how much nicer life is going to be. And they're tedious, but it'll be very similar to what we just did. They don't get any worse than that. I think one of them is a quadratic and one is a linear equation. So the linear equation will be a little bit less work. The quadratic will be very similar to what we just did. So give them a try. Remember, 5.1 and 5.2 are fairly tedious sections, but once you get to 5.3, then we'll learn all the shortcuts. So give it a shot. Let me know if you have any questions.